Hey everyone, it's Dr. C. Happy Real Friday. It is Friday, not Chem Friday. Thanks for a good first week. I think we got off to a great start. And let's continue. One thing that I don't like about Tuesday, Thursday classes is I don't see you from Thursday a lot of times all the way to Tuesday unless you come to office hours or something else along the way. So this is a nice way for us to at least communicate a little bit in a certain way between Thursday and Tuesday. So in the two sections, the 11:10 section, I got a little bit farther on Thursday than I did in the 12:45, but we were pretty close. And so let's just start here. In the 11:10, we did start talking about the second law, but let's just back up a little bit. It won't hurt to do a little review if you're in the 11:10 section. So as we've talked about, the main goal of this chapter is to determine if a reaction is spontaneous. All right, to determine spontaneity. All right, and we're going to do that two different ways. And the first way we're going to do it is the second law of thermo. And so let's focus on that in this pre-lecture. We will get to Gibbs free energy later. All right, but let's focus on the second law of thermo. And the second law of thermo can be stated pretty simply as the following. The entropy of the universe is always increasing. And maybe you've heard that before. All right. Another way to be a little bit more specific than that is to say that entropy of the universe increases in a spontaneous process. And sorry about my writing. I'm not doing a very good job of being neat here, so let me see if I can do a little bit better. All right, so in a spontaneous process, the entropy change of the universe is going to be positive, greater than zero. Okay, so that's what we're shooting for. We're actually going to do a calculation in this pre-lecture where we calculate the entropy change of the universe and predict spontaneity based on that. Okay, so that's the second law. The entropy of the universe is always increasing, or we can be a little more specific and say entropy of the universe increases in a spontaneous process. Delta S universe is positive. Now, as you probably know from last semester, the universe is made up of the system and surroundings. And for us, our system is typically our reaction, and then everything else is the surroundings. Okay? So, second law only focuses on entropy. Now, you might be thinking, well, Dr. C, we've spent a lot of time so far this semester on enthalpy. Where does that come in here? And it is here. It's just kind of buried in this equation. So let's talk a little bit about enthalpy of the system, the reaction, and entropy of the reaction, and then we're going to put those together into this equation. But what I want you to start thinking about, and I apologize, I'm getting some feedback on my microphone here, so I hope that's not completely annoying you. So let's talk about delta S of our system. And again, we use reaction and system interchangeably. All right. Exothermic, which has a negative sign for delta H, exothermic reactions tend to be spontaneous. Or another way to say that, in terms of heat flow, in terms of favoring spontaneity, exothermic reactions are favored or are favorable, depending on how we want to say it. Okay, so in terms of heat flow, reactions that release heat are favored. That's the direction of heat flow that favors a spontaneous process. For the entropy change of the system, reactions that lead to more dispersal of energy, a greater entropy, or we can think of it as reactions that lead to more disorder, those are favored. So increase in entropy more disorder, more dispersal of energy. Those are favored. That's a positive delta S. Now, there's a lot of signs going on here, so try to wrap your head around all these sign conventions. There's a lot of them. That's favorable. Okay? So what I want you to start thinking about is if your heat flow is favorable, exothermic, and your entropy change is favorable, increase in entropy, positive, that type of process will be spontaneous. Both things are working for you there, right? So we said, or at least we've been trying to get to this point, there's two things we need to look at for spontaneity: heat flow and entropy change. All right? And this is focusing on the reaction. If they're both good, that's terrible wording, but if they're both favored, then the reaction's spontaneous. So if you have this situation, we can right away say this is spontaneous. And I apologize, I kind of squeezed that in. So keep that in mind. We're going to keep coming back to that. Now, how does that delta H, exothermic, tie in with our surroundings? And we did just start talking about this in class on Thursday. So let's focus on a reaction that we know is exothermic. Let's focus on a combustion reaction. All right. So we know this is the combustion of propane. We know this releases heat. We know delta H is exothermic. All right. Well, now let's look at our entropy change. And we don't even have to calculate it here. Let's just look at it. We go from 6 moles of gas to 7 moles of gas. The amount of particles of gas is increased. There's energy is going to be more dispersed over that increasing number of particles. We can think of that being more disordered because there's more particles moving around. Any way we think about this, we get an increase in entropy from 6 moles of gas to 7. So look at those two sign conventions. Exo, favorable. Increase in entropy, favorable. Boom. Spontaneous. Okay? So we're going to keep working on that. Now, again, I keep going back. Well, we need to get back to the second law. We need to get back to the second law. How does that play in here? So here's our second law. Delta S of the universe is equal to the system and the surroundings. All right? For the combustion of propane gas, we just saw that, again, the system is our reaction. That's positive. We go from 6 moles of gas to 7. Now, this is from a book. It's already labeled delta S of the surroundings as positive. Why would that be positive? And we did talk about this a little bit in class on Thursday. Remember, combustion... Oh, I'm sorry, there's that feedback again. I don't know why it's doing so much of that today. I'm hoping I'm hearing it more on my end than on your end. So, exothermic combustion reaction, that heat is going to flow from the system to the surroundings. So what is that additional energy, thermal energy, which is a kinetic energy, going to do to the surrounding particles? Yeah, it's going to speed up the motion of those surrounding particles. Okay? So right away we start, things are going to speed up, they're going to collide more, whatever. That is an increase in entropy. We also know that entropy does increase with temperature. As we raise the temperature, the entropy is going to go up. So because the reaction is exothermic and the heat flows out to the surroundings, that increases the entropy of the surroundings. Okay? So, in this case now, we've tied in our heat flow to the surroundings. What does that heat flow do to the entropy of the surroundings? If both of these are positive, then delta S of the universe is positive. What does the second law say? The entropy of the universe increases in a spontaneous process. Boom, spontaneous. Okay? So when you look at this equation, delta S universe is equal to delta S system plus delta S of the surroundings, it initially looks like heat flow's not in there, but it is. And the heat flow is going to impact the surroundings. If it's exothermic, it's going to increase the entropy of the surroundings. If it's endothermic, it's going to pull kinetic energy, thermal energy out of the surroundings and decrease the entropy of the surroundings. So we'll look at that a little bit more as we go on. But let's see how we're actually going to calculate delta S of the surroundings. Okay, and as we saw, it is proportional, this means proportional here, to the entropy change of the system. And we do have to put a negative sign there because think about your sign convention. If our delta H is negative, exo, right, negative times a negative, that's going to be an increase in the entropy of the surroundings. So that's why we need a negative sign in front of the delta H. And here's just kind of a nice image to take a look at really quick. This one on the left is showing heat flowing out of the heat flowing out of the system to the surroundings, and that's going to increase the entropy of the surroundings. Conversely, if we pull energy out of the surroundings, so pull heat out of the surroundings into the system, the entropy of the surroundings is going to decrease. So that's important to know that, and we'll see that in this equation. And I'm having trouble finding my cursor. Let's scroll one more. Oops. I didn't want to get to that yet because I want to focus on the propane system, and I, of course, went too far. All right, now there's one more thing that comes into play, and I'm just going to touch on it briefly here. The temperature of the surroundings is going to come into play as well. If the surroundings are at a really low temperature, any heat flowing out of the system is going to have a much bigger impact on the surroundings. All right? If the surroundings are at a high temperature and that same amount of heat flows out of the system, it's not going to have as big of impact on the surroundings. Okay, so think about that a little bit. If the surroundings are at quite a low temperature, any heat coming out of the system is just going to have a much larger impact on the surroundings. So to make this equation, well, that's not an equation yet, but to make it an equality, we have to add one more thing. We have to add temperature. And it's inversely proportional to the temperature. Lower temperature, smaller number here, the heat flow is going to have a bigger impact on the surroundings. If the temperature of the surroundings is higher, then we're dividing by a larger number. The heat flow is going to have less of an impact on the surroundings. So where does this take us? This takes us to, gosh, I have no idea why my microphone's feeding back so much. And I hope you're thinking I'm just being silly and you're not hearing this. We can take that equation, delta S system plus delta S surroundings, and we can modify it. Because we now know that we can calculate the entropy of the surroundings using the delta H of the system and the temperature. Okay? So that's how we do the calculation. And I'm going to do one in just a minute, but I'm going to do it for a slightly different system. Well, actually for quite a different system. We're going to do a different reaction. We don't need to calculate delta S universe for the combustion of propane. Do you agree with that? Think about it. Yeah, we don't need to do a calculation because we know it's spontaneous. Right? Exothermic, favorable heat flow, increase in entropy of the system because we go from 6 moles of gas to 7. It's got to be spontaneous. We don't even need to do a calculation. Or we can think of it as looking at the second law. 6 moles to 7 moles is your system, positive delta S of the system. Because it's exothermic, it's going to increase the entropy of the surroundings, both positive, always spontaneous. So in that case, we don't even have to do a calculation. Let's look at one where we have to do a calculation. That's where we'll wrap up. And I know I've gone for about 13 or 14 minutes, so I'm going to try to wrap this up. Freezing of water. And we'll try to do this one pretty quickly. Spontaneous? Yeah, it depends. It depends on temperature. So what we're going to find is if we have one favorable quantity and one unfavorable in terms of delta H and delta S of the system, it will depend on the temperature whether or not it's spontaneous. And that's what this graph is trying to show. It's trying to show at low temperature, we know water freezes. If we're below the freezing point, we're going to end up with a positive delta S universe. If we're at a higher temperature above the freezing point, we're going to end up with a negative delta S universe. And we're going to do a calculation in just a minute. But why is it temperature dependent? Well, freezing of water, we're going from H2O liquid to H2O solid. So what is your entropy change for that system, that reaction? Not the number, but what is the sign? We go liquid to solid. Yeah, that's a decrease in entropy, negative. Okay? Now, what about delta H for that system? Now, this is where you have to think system to surroundings, okay? Because you don't think of the freezing of water releasing heat. But to get water to freeze, we've got to get energy out of the liquid. Remember, those liquid water molecules are moving, so think on a molecular level. Try to visualize it. Those water molecules are attracted to each other, but they're rolling over one another. There's motion. We've got to get kinetic energy out of that system. We've got to slow those water molecules down. We've got to get thermal energy out. How do we do that? Well, we typically put the water in a cold environment, right? In the freezer, say. But heat needs to be taken out of the system to the surroundings. System to surroundings, that's exothermic. Okay? So what we have here is a favorable heat flow, but an unfavorable entropy change. And if you have one favorable and one unfavorable, it's going to be temperature dependent. Okay? And if you don't quite get all of this right now, that's okay. This is just our start. We'll do more in class. But keep in mind, think favorability for delta H of the system and delta S of the system. Exothermic is favorable. Increase in entropy is favorable. Here we have the exothermic, but we have a decrease in entropy. One favorable, one unfavorable, temperature dependent. So let's wrap this up with a calculation. Let's see how we would do this. I'm just going to give the values of delta H and delta S for this process. Delta H for this process is negative 6.01 kilojoules, exothermic, and delta S is also negative 22 joules per Kelvin. All right, and now let's plug into our second law. Let's substitute in for delta S of the surroundings. Okay, now we can plug in delta S. Oh gosh, I'm sorry. Delta S of the system. Oh, I know why it's doing it. I thought I had muted my microphone on my computer, which I did not, and I always do that before I record, or almost always do that. All right, now let's plug in delta S of the system. Now, you should know how to calculate these by now. We could have calculated these from delta H formation values and standard entropy values. But I decided for sake of time, let me just give you those values. So make sure you know how to calculate those. Let's plug them in. Now, let me choose a temperature, because I didn't put a temperature. Let's choose a temperature where we know this is not spontaneous. Freezing of water is not spontaneous at room temperature. All right. Now, you do have to have, notice Kelvin. We do have to have our temperature in Kelvin. So that is 298 Kelvin. And we do have a negative sign there, and it was a negative delta H. So negative of a negative, that's going to be a positive. Okay? Now, what do you notice about your units? Yeah, we have joules here, and we have kilojoules there. So we're going to have to take care of that. Now, the quick way, and again, I've gone a little bit longer than I wanted to, I know kilo means 10 to the third. Okay? And let's just, if I can get this to work, I'm just going to cross that out. Kilo means 1,000, so I'm just going to write 6.01 times 10 to the third joules. Quick way to convert my kilojoules to joules. Okay, now let's do our calculation. Take 6.01 times 10 to the third and divide it by 2.98, or 298, 2.98, 298. You should get about 20.2 positive, but now we're going to add that to negative 22, and we end up with about a negative 1.8 joules per Kelvin. That is for delta S of the universe. Okay, so what does the second law of thermodynamics tell you? Entropy of the universe increases in a spontaneous process. This is a decrease in entropy of the universe, so this would be non-spontaneous. And we know that, right? We know water does not freeze at room temperature. So what I want you to try is repeat this calculation at a temperature below the freezing point. You know, choose like negative 20 Celsius or negative 50 Celsius. Pick a number that's below 0 Celsius. Okay? Make sure it's in Kelvin, and then see what you get for delta S of the universe, and you should get a positive delta S universe. So try that. Do one more calculation just to prove to yourself you can do this equation. But again, systems or reactions where we have favorable heat flow and unfavorable entropy change, or vice versa, if we have one favorable and one unfavorable, those will depend on temperature. And we do need to calculate, are they spontaneous at that temperature? Okay, sorry, I think I went about 20 minutes, a little bit more than I wanted to, but this introduces us to the second law. It is one way, one method that we're going to use to predict spontaneity of a reaction. So watch for the pre-lecture quiz coming up. Make sure you know the definition of the second law. Make sure you know, do you want a positive delta S universe? Do you want a negative delta S universe for spontaneity? Also make sure you can do a calculation like the one that we did here with given a delta H of the system and a delta S of the system, can you get delta S of the universe? Okay. Hope these pre-lectures are working for you. Let me know if you'd like me to do something different. And I will see you in class on Tuesday. Take care.